Forget everything you thought you knew about how we see the universe. For centuries, light was our only messenger from the cosmos. But what if there's a different kind of signal, one that lets us hear the scream of black holes as they merge, or witness the birth of a new universe? Get ready to discover gravitational waves, the groundbreaking new way we're eavesdropping on the universe's most violent events. Beyond the visible, a new sense for the cosmos. Close your eyes. Picture space-time not as emptiness but as a flexible fabric. Drop a mass on it and the fabric warps. Jostle that mass violently and ripples race outward. Those ripples are gravitational waves, teeny, passing stretches and squeezes of space-time itself. Traveling at light speed, they don't shine, they don't scatter, they simply move through everything, changing distances by a whisper. Unlike light, which can be absorbed, blocked, or muddled, gravitational waves pass almost unhindered through stars, gas, and dust. They carry pristine fingerprints of the cataclysms that made them, colliding black holes, merging neutron stars, supernova, and perhaps even the first instance after the Big Bang. In practice, what we measure is the strain, the relative change in length, h equals delta L. L for astrophysical events reaching Earth. H is often around 10⁻21, a change smaller than a proton's width over kilometers. Key concepts to keep in mind: ripples in spacetime, not in a medium, but of the geometry itself. Polarizations, waves, stretch one axis while squeezing the perpendicular one. The pattern flips 45 degrees for the second polarization. Transparency, they offer a view into regions that light cannot escape. Einstein's prophecy, from theory to reality. In 1916, Einstein's general relativity predicted that accelerating masses would emit gravitational waves, with the strongest emission from changing quadrupoles. Think of two dense bodies orbiting and pulling space-time tight in one direction, slack in the other. For decades, many doubted we could ever detect such minute effects. Then came a clue, a binary pulsar whose orbit shrank over time exactly as gravitational radiation would siphon energy away. The universe hinted, detectors had to listen. The challenge bordered on absurd. To sense HSIM 1021 across a 4 km instrument arm, you must measure changes of about 4 × 10⁻18 m, less than 1,000th the size of a proton. Earth itself is noisy. Traffic rumbles, ground tilts, atoms jiggle, lasers flicker. Turning theory into measurement meant bending engineering to the edge of possibility. Silence the Earth, still the light, and balance mirrors so perfectly that space-time's faintest tremor stands out. Educational takeaway: quadrupole radiation. Dipoles can't emit gravitational waves. Mass energy is conserved, so the simplest radiating pattern is quadrupolar. Energy loss in binaries. Careful timing of pulsars offered indirect proof long before direct detection. Scale of the signal. Gravitational wave astronomy is precision metrology at cosmic stakes. LIGO and Virgo, Earth's ears for space-time. Imagine an L-shaped ruler made of light. This is a laser interferometer, a laser beam split into two 4 km arms, bouncing between near-perfect mirrors in vacuum, recombining to create an interference pattern. A passing gravitational wave slightly stretches one arm while squeezing the other. The recombined light brightens or dimmed by an amount telling you how space-time moved. That's LIGO in the United States and Virgo in Italy, machines tuned to hear the universe. How it works. Simplified. Laser interferometry, a beam splitter, sends light down to perpendicular arms. Path length differences shift the interference at the detector. Test masses. Mirrors hang as multi-stage pendulums to isolate them from seismic and thermal noise. Noise hunting. Engineers tame seismic rumble at low frequencies, quantum shot noise at high frequencies, and thermal vibrations in between. Matched filtering. Computers compare data to a bank of predicted waveforms, pulling faint chirps from the static. On a September day in 2015, LIGO caught a rising chirp, a frequency sweeping up and then cutting off. It was the death spiral of two black holes, spiraling together faster and faster until they merged and rang like a struck bell. No light, no image, just a note that said, "This is real." Math moment. The chirp tracks, the chirp mass mathcal m equals meter_1 m_2 3/5 meter_1 plus m_2 1/5. From the frequency's rise, we infer the masses and distance, unveiling the universe's extreme events. The black hole ballet is silent to telescopes, but musical to spacetime. We hear the inspiral, a clean, rising tone, the merger a brief, violent crescendo, and the ringdown a decaying hum as the remnant settles. From these phases we test general relativity and probe black hole spins, masses, and the very geometry of horizons. Each detection is a laboratory with gravity turned to maximum. Then came neutron star smash-ups, cosmic collisions of city-sized sun-mass nuclei. Gravitational waves announced the merger. Telescopes worldwide pivoted to catch the afterglow. The result, a kilonova, a radioactive bloom forging heavy elements via rapid neutron capture. Gold, platinum, strontium, the glitter in our jewelry, and the atoms in our electronics, born in the wreckage of neutron stars. For the first time, gravitational waves and light together told a single story across the spectrum. Multi-messenger astronomy had arrived. Why this matters. Invisible made visible. Black hole mergers are dark in light but bright in gravitational waves. Origins of elements. Neutron star mergers explain much of the universe's heaviest elements. Cosmic rulers. Gravitational waves act as standard sirens, letting us estimate distances directly and refine cosmic expansion measurements. The future of gravitational wave astronomy. The orchestra is growing. LIGO's twin observatories, Virgo in Italy and Kagura in Japan, already collaborate. An upcoming detector in India will add another ear, improving sky localization. Next-generation ground detectors. Cosmic Explorer and Einstein telescope aim to push sensitivity deeper, hearing farther and fainter, from the nearby universe to billions of light-years away. In space, the Laser Interferometer Space Antenna LISA will float a triangle of spacecraft millions of kilometers apart, listening to lower frequency waves inaccessible from Earth. Supermassive black hole mergers, compact binaries in our galaxy, and perhaps whispers from new physics. Even grander baselines. Pulsar. Timing arrays use millisecond pulsars as cosmic clocks, sensing nanohertz waves from gargantuan black hole pairs in distant galaxies. Together, these bands form a spectrum of gravity's music, from bass rumbles to treble chirps. Frontiers on the horizon. Primordial waves. Fossil ripples from inflation could reveal the universe's first fractions of a second. Exotic compact objects. Boson stars, cosmic strings, or deviations in ringdowns might hint at physics beyond general relativity. Precision cosmology. Standard sirens, combined with galaxy catalogs, can sharpen our measure of the Hubble constant and test dark energy models. Educational notes. Frequency bands. Ground detectors approximately 10 to 1000 Hz. Polarization tests. Measuring the allowed polarizations. Probes the geometric structure of gravity. Data deluge. Machine learning and massive template banks sift subtle signals from noise at scale. Our cosmic soundtrack. We used to think the universe revealed itself only to eyes human or mechanical. Now, with gravity as our guide, we hear the cosmos play its most secret songs. Black holes, duetting in darkness. Neutron stars screaming into light. Galaxies humming with ancient tension. Each detection is a new instrument added to the symphony. Each upgrade a fresh octave unlocked. We are early in the concert. The score is vast. Somewhere a supermassive pair is tuning up. Somewhere else, a relic wave from creation waits just above our noise. When we listen together across continents, across disciplines, across messengers, we don't just learn what the universe is, we remember that it can still surprise us, and that we now have the ears to be surprised.